Hello there, welcome to my class. Today we'll talk about...
Good day everyone. In this video, we'll try to use multiplexers in implementing Boolean expressions. We are given the function a, b, c, d equivalent to the summation of 0, 3, 4, 5, 9, 12, and 13. How are we going to implement this using multiplexer? First thing that we have to know is what multiplexer are we going to use? Is it 4 by 1, 8 by 1, 32 by 1, a multiplexer? To know what multiplexer we are going to use, let's consider the number of literals. In this equation, there are 4 literals, A, B, C, and D. Subtracting 1 from it becomes 3, and 2 raised to 3 will be equivalent to 8. We'll be needing, therefore, an 8 by 1 multiplexer. So how are we going to use a multiplexer? Using this table, since there are 8 inputs, we'll be needing this table. It has 8 inputs, I0 to I7. And for us to have 8 inputs, we'd be needing 3 literals. So that is A, B, and C. Because 2 raised to 3 again is equivalent to 8. Considering that there are 4 literals in our function or Boolean expression, the other literal will be put here. We try to find the value of the different locations in our truth table. Since this is I0 and I0 will be selected when A, B, and C is equal to 0, 0, 0. And D is also equal to 0. So therefore, this is equal to 0. How about this? It becomes 0, 0, 0. D is equal to 1. So therefore, this will be equal to 1. This one will be equal to 0, 0, 1, 0. And that is equal to 2. 0, 0, 1, 1. That will be equal to 3. Until such time that we reach 15. That is equal to 1, 1, 1. And D is also equal to 1. Therefore, it's equal to 15. How are we going to get the equation for our multiplexer? Let us first put our mean terms in our table. For example, 0, so this will be 0. Then we have 3, 4, and 5, 9, 12, and 13. From these combinations, or mean terms, we will derive now our equation. Since I0 is equal to D prime, and D has no mark, then this will be equal to D prime. At I1, our mark is at D, therefore it will be equivalent to D. At I2, that will become D prime and D, that will be equal to 1. No mark will be equal to 0. This will be again equal to D, and this will again be equivalent to 0. This again will be D prime plus D is equal to 1 from our Boolean algebra, and this will be equivalent to 0. So let's try now to implement this equation using a multiplexer. As we said a while ago, we'll be using 8 by 1 multiplexer. Our select pin, which we use here to select I0 up to I7, is will be connected to A, B, and C. How about our input I0 to I7? Our input I0 to I7 will be connected to our derived value from our table. For example, I0, as we said a while ago, since it's connected only to D prime, then this becomes D prime. I will clarify why is this equal to 1. This is equal to 1 because for I2, we have a mean term for 4 and 5, and that will be equal to D prime plus D. And we know that D prime plus D would be equal to 1 as per our Boolean algebra. I0 will be connected to D prime, whereas I1 and I4 will be connected to D. I2 and I6 will be connected to 1. How are we going to ensure this will be equivalent to 1? By connecting it to VCC. Whereas I3, I5, and I7 is equivalent to 0. It can be achieved by connecting it to ground. So let's try to simulate our circuit whether it is able to implement the equation function A, B, C, D is equivalent to the summation of 0, 3, 4, 5, 9, and 12, and 13. Let's try to simulate the values 3, 7, and 13. So if we have the value for 3, that will be equivalent to 0, 0, 1, 1. Meaning to say, ABC therefore will be equal to 0, 0, 1. ABC will be equivalent to 0, 0, 1. And with that, we'll be selecting I1. And I1 is connected to D. What's the value of D? D is equal to 1. Therefore, our output will be equal to the value for D, which is 1. Is that correct? 3 will be equal to, our function F will be equal to 1 with an input equivalent to 0, 0, 1, 1. So since 3 is in our equation, it will be equivalent to 1. Let's try 7. 7 is 0, 1, 1, 1. ABC, which is connected to our select pin, will be 0, 1, 1. ABC is 0, 1, 1. With that, we'll be selecting input 3. And input 3 is connected to ground, therefore F will be equal to 0 no matter what is the value for D. Since it is not I4 or I1 that is selected, but rather it is I3. Let's try to implement also a full adder using a multiplexer. We have already implemented a full adder before using a decoder. Let's try to implement it also using a multiplexer. We are given the truth table for a full adder. To review, since it's a full adder, it will add 3 bits. And as we can see, if we add 0, 0, 0, that will be a carry of 0 and a sum of 0. 0, 0, 1 will be a sum of 0 and carry 1. 0, 1, 0 will be a sum of 0, carry 1. 0, 1, 1 will be a sum of 0, carry 1. 1, 0, 0 will be 1, carry 0. 1, 0, 1 is 0, carry 1. 1, 1, 0 is 0, carry 1. And 1, 1, 1 is equal to the sum of 1, carry 0. So let's try to implement this using a multiplexer. In doing so, what multiplexer are we going to use? Since there are 3 inputs, minus 1 will be 2. 2 raised to 2 will be equal to 4. Therefore, we'll be needing a 4 by 1 multiplexer. So let's now have our table to extract simplified equation for the implementation of the multiplexer. Allow me to use this time BC to be the input for our select pin, and A will be used for our input I0 to I3. Let's try to compare this with what we did a while ago. When we tried to implement the function ABCD is equal to this equation, I selected A, B, and C to be connected to our select pin, and D will be connected to I0 to I7. This time, what I did is to use BC to be connected to the select pin, and A here will be the one to be connected to the input. Try to compare the location of our boxes with respect to the two tables. Here, A will be 0, so therefore 0, 0, 0, that is 0. This one will be A is 0, then 0, 0, 1 will be 1, 0, 1, 0 will be 2. Whereas on the other table, which we used a while ago, this will be 0, 0, 0, 0. So this is 0. This one will be 0, 0, 1. Not like here anymore. This is 1, 0, 0. Therefore, this is already 4. Here, it will be vertical, going horizontal. Whereas here, numbering will be horizontal. Do remember how we arrive with the arrangement of our numbers in our table, considering the location of the inputs that we use in our table. Let's try now to derive the equation for our sum. Our sum will be at 1, 2, 4, and 7. So 1, 2, 4, and 7. Therefore, our equation will be A prime, then another A prime, and this one is A. How about our carry? Our carry will be 3, 5, 6, and 7. So therefore, 3, 5, 6, and 7. So it will be 5, 6, 3, and 7. The equation therefore will be, here will be 0. This will be A, this will be A, and this will be equal to 1. So let's try now to implement our equation for the sum and the carry. So for the sum, I0 and I3 will be connected to A. So we'll be using a 4 by 1 multiplexer. The select pin is connected to B and C, whereas I0 and I3 will be connected to A, and I1 and I2 will be connected to A prime. How about our carry? We'll be also using a 4 by 1 multiplexer. I0 will be connected to ground, whereas I1 and I2 will be connected to A, and I3 will be connected to VCC. Let's try now to simulate an input. Let's choose, for example, 2. 2 will be 0, 1, 0. That will give us a result of a carry of 0 and a sum of 1. 0, 1, 0. BC is 1 and 0. So what will be selected is I2, and A is connected to 0. So since A is equal to 0, therefore our carry is equal to 0. A is equal to 0, inverted, entering into I2 will be equal to 1. So therefore sum is equal to 1 and carry is equal to 0. Is that correct? Sum is equal to 1 and carry is equal to 0. Let's try 5. 5 will be 1, 0, 1. So BC again is 0, 1, 0, 1. So since it's 0, 1, what will be selected is I1, both I1. A is equal to 1. So since I1 is selected and A is equal to 1, this will be equal equal to 1. Whereas this one, A is equal to 1, inverted will become 0, therefore our sum is equal to 0 and our carry is equal to 1. Is that correct? Our sum is equal to 0 and the carry is equal to... Let's try another. That is 7, 1, 1, 1. So BC will be 1, 1. Selected will be I3. It's connected to BCC, therefore this is equal to 1. I3 is connected to A, and since A is connected is 1 also, then this will also be equal to 1. The sum and the carry is equal to 1, 1. Again, try to simulate the other input to check whether our circuit is functioning or designed proper. In summary, we tried to implement full adder before, and we used 2 half adders and an OR gate. Then we use a 3x8 decoder with 2 OR gates, the output. This time, we are now trying to use a multiplexer. So, what's the difference? In using a multiplexer, a dual 4x1 multiplexer can be put in a single package. Meaning to say, we may be able to implement full adder using only a single integrated circuit. If we use ordinary gates, there will be more integrated circuits that will be used. Same as that with our octal decoder because of the presence of the 4 input OR gates at the. Does not mean, however, that it would be better to use a multiplexer. But does this show us? It would only show us that there are other ways to implement a circuit, not only using ordinary logic gates, but we can also use decoders and multiplexers. In the implementation, therefore, or Boolean expression, do remember that we are not limited only in using ordinary gates, but we may be able to use other integrated circuits like multiplexers and decoders. Thank you once again and enjoy designing more digital circuits.